Now it is not at some distance from the center. It is at the center itself. Field on the axis of a circular coil. When I consider a point, what is the shape of the conductor given? Sir, it is a circular loop. On the two ends of the axis, magnetic field decreases. They are present on the two opposite diametric ends. So magnetic field at a point on the axis Hello students, how significant was my previous session on moving charges? What did you all learn from that session? Sir, we understood a very interesting law, Biot-Savart's law, Laplace's law. Dear children, what was the significance of Laplace's law? We can find the strength of the magnetic field at some distance away from a current element. And what was the general formula for magnetic field? dB equals mu naught divided by 4 pi idli sin theta divided by r square. Tasted that idli? Very beautiful. Then what is that I have in store today in my session 5? We will see the application of that idli, which means we will understand one application of Biot-Savart's law, the so-called Laplace's law. Now, what is that I object doing in today's class? In my today's session, as I told, I will use Biot-Savart's law. I will use Laplace's law to derive an expression for magnetic field at a point on the axis of a circular loop carrying current. One interesting fact about this derivation, this is one of the most favorite question of any question paper setter from 2nd PUC physics. Ideally, the most frequently repeated question for 5 marks. Closing your eyes, you can take this to be one of the 5-mark questions for your exam. So what is that I am doing? I am deriving an expression for magnetic field. The strength of the magnetic field by considering a point on the axis of a circular loop. The shape of the conductor is clearly mentioned. It is a circular loop, circular coil, not a straight conductor. It is a circular coil carrying current, circular loop carrying current. So magnetic field at a point on the axis of a circular loop carrying current. And again I repeat, students, this is ideally application of Biot-Savart's law. Again, a flavor of having idli sin theta. Fine. To begin with, as usual, let us go to our assumptions. I will consider a circular loop of radius r carrying a current I. ಒಂದು ಸರ್ಕ್ಯುಲರ್ ಲೂಪ್ ಇದೆ. ಇದನ್ನ ಸರ್ಕ್ಯುಲರ್ ಕಂಡಕ್ಟರ್ ಅಂತ ಕರಿತೀನಿ. A circular loop whose radius is r and I is the current which is flowing through that loop. O is the center of this circular loop. Very simple. What is the shape of the conductor given? Sir, it is a circular loop. Very good. In circular loop andre, it is a circular coil. What is its radius? R. What is the current flowing through the coil? I. What is its center? O. Fine. Now what do? I will consider a point P at a distance x from the center. Some point P at a distance x from the center O. Why do I require that point? It is at that point P I am calculating the magnetic field. So dear students, where am I calculating the magnetic field? It is at the point P at a distance x from the center of the coil. And what do I apply to calculate the magnetic field? Biot-Savart's law, Laplace's law. So by using Laplace's law, I am calculating the magnetic field at the point P. If I need to apply Biot-Savart's law, what do I require? Current elements, sir. Very good. So I require current element to apply Biot-Savart's law. So I consider a thin current element AB whose length is dl. A very thin, please do keep in mind, a thin current element AB whose length is dl. One more current element A dash B dash whose length is again dl. So I say AB and A dash B dash are the two diametrically opposite current elements. I repeat that word. Diametrically opposite current elements. Two elements present on the opposite ends of the diameter. Observe Madi, this is AB whose length is DL. A dash B dash whose length is DL. They are present on the two opposite diametric ends, and each current element is at a distance A from the point P. Both the elements are at a distance A from the point P. So, very simple is my assumption. Dear students, ಯಾವ ರೀತಿಯಾದಂಥ shape ಇದೆ ಇಲ್ಲಿ? It is a circular loop, circular coil whose radius is R. I is the current which flows through the conductor. Where am I calculating magnetic field? At the point P. What is its distance from the center of the coil? X. Very simple. P is at a distance X from the center. Which are the two current elements? A dash, B dash of length DL. A, B of length DL. So there are two elements diametrically opposite to each other. Very good. And both of them are at a distance A from the point P. Now, my first step of calculation, very simple. You have a right-angled triangle here, a triangle in the shape of a right-angled triangle, where I know A square should be equal to R square plus X square, by using our Mr. Pythagoras' famous theorem. A square is R square plus X square. Now, writing it in indices form, A equals R square plus X square to the power half. Next calculation. This angle is alpha. So sin alpha is calculated as opposite side by hypotenuse. So sin alpha equals R divided by A. So two preliminary steps of calculation I have done, where I told A square equals R square plus X square. Who told that? Our ancestor, Mr. Pythagoras, a strong mathematician. A is therefore R square plus X square to the power half. And from the triangle, what is sin alpha? Opposite by hypotenuse, R divided by A. Fine. Shall we proceed? Yes. Now, students, I will calculate the magnetic field at P due to the element AB. Observe ಮಾಡಿ clean ಆಗಿ. In this step, I am calculating the magnetic field at P due to this element AB. The very first application, magnetic field at P due to the element AB. How do I calculate that? Biot-Savart's law. We're generally told dB equals mu naught divided by 4 pi I dl sin theta divided by r square. That is the general form of Biot-Savart's law. dB equals mu naught divided by 4 pi I dl sin theta by r square. Here the whole game is to understand what is theta and in general what is r. If you recap to my previous session, what is theta? It is the angle between the element and the line joining the element to the given point. Most of the times you get confused and you think this is theta. No. What is theta by description? Theta is the angle between the given current element and the line which joins the element to the given point. How much it is? 90 degrees. How is it possible? That is why I told the element has to be selected to be very, very thin, so that it forms a tangent to the given surface. So it is forming a tangent to the given surface. So the angle between the tangent and current flowing in the plane becomes 90 degrees. Just go back to your regular geometry. I have considered the element to be very, very thin, very possible thin element, so that it behaves as a tangent to the surface, and the angle between the tangent and the current flowing through that surface is 90 degrees. Or rest assured, just consider theta to be 90 degrees. And what is the distance between the element and the point? A. So r square is there. So this becomes a square. So dB equals mu naught by 4 pi I dl. Now sin 90 is 1 divided by a square. And very importantly, the magnetic field is acting along PM. Andre, the magnetic field at this point P due to the element AB is acting along PM. So this is the direction of the magnetic field dB at P due to the element AB. Similarly, friends, magnetic field at P due to the element A dash B dash. Again the same application. Again theta is 90 degrees. Again the distance is A. So again the magnetic field dB equals mu naught by 4 pi ideal A square. But now this is acting along Pn. So the magnetic field at P due to the element A dash B dash is acting along Pn. So ನೀವು ಇಲ್ಲಿ ಏನು ನೆನ್ಪಿಟ್ಕೋಬೇಕಂದ್ರೆ magnetic field at P due to the element AB acts along Pm. Magnetic field at P due to the element A dash B dash acts along Pn. Now, this is the core of the derivation. Very important. Magnetic field along Pm is resolved into two components. Resolve ಮಾಡೋದು ಅಂದ್ರೆ ಏನರ್ಥ? The very word resolve means to break. The magnetic field which was acting along Pm ಡೈರೆಕ್ಷನಲ್ಲಿದ್ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡನ್ನ ಎರಡು ಕಾಂಪೊನೆಂಟ್ಗಳಾಗಿ ಬ್ರೇಕ್ ಮಾಡಿದ್ದೀನಿ. I have resolved the magnetic field along Pm into two components. That is, if you observe, again with respect to this alpha, now this magnetic field is getting resolved into two components. Which are those two components? The first component is dB cos alpha along the direction Py and dB sin alpha along the direction Px. First year PUC nalli resolution of vectors odirtira with respect to the angle along the horizontal and along the vertical, breaking up of vector components ant helirtivi. Here, what is getting resolved? What is getting broken? Magnetic field which is acting along the direction Pm into two components. ಯಾವ್ದದ ಎರಡು ಕಾಂಪೊನೆಂಟ್? dB cos alpha along Py, dB sin alpha along Px. Similarly, magnetic field along Pn is also resolved into two components. The magnetic field that is acting along Pn is also resolved into two components. Again, which are they? Again, dB cos alpha along Py dash, dB sin alpha again along Px. Therefore, I have written here along Py axis dB cos alpha, Px axis dB sin alpha. Again, along Px dB sin alpha, Py dash dB cos alpha. Now, if you observe the diagram carefully, two components get cancelled each other. ಆ ಡಯಾಗ್ರಾಮ್ ಅನ್ನ ಕೇರ್ಫುಲ್ ಆಗಿ ಅಬ್ಸರ್ವ್ ಮಾಡಿದ್ರೆ ಎರಡು ಕಾಂಪೊನೆಂಟ್ಗಳು ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ವಿಚ್ ಆರ್ ದೇ? ಎವಿಡೆಂಟ್ಲಿ dB cos alpha along Py, dB cos alpha along Py dash. They cancel each other. Why do they cancel each other? Because they have the same magnitude but they act in opposite direction. Alva? ಎಷ್ಟು ಬ್ಯೂಟಿಫುಲ್ ಆಗಿದೆ ನೋಡಿ. One component is acting along Py The other component is acting along Py dash, but both the components have the same magnitude. Idu dB cos alpha, idu dB cos alpha. Eradaru magnitude ಒಂದೇ ಆಗಿದೆ, but they are acting in opposite directions, so they cancel each other. So what is the remaining magnetic field? Or in other words, what is the net magnetic field at P? dB sin alpha plus dB sin alpha. So the net magnetic field along P is 2 dB sin alpha, which is acting along Px. dB cos alpha, dB cos alpha cancel ಆಗೋಯ್ತು. ಉಳ್ಕೊಂಡಿದ್ದೇನು? In the direction Px, dB sin alpha plus dB sin alpha. So it was 2 dB sin alpha along Px. Now I have arrived at 2 dB sin alpha, which is the resultant magnetic field at P, considering two opposite current elements only. A pair, two opposite current elements. Now if the entire coil is made of such opposite current elements, ಎರಡು ಕರೆಂಟ್ ಎಲಿಮೆಂಟ್ಗಳನ್ನ ಕನ್ಸಿಡರ್ ಮಾಡಿ ನೆಟ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನು ಸಿಕ್ಕುತ್ತೆ? 2 dB sin alpha. ಅದೇ ಇಡೀ ಕಾಯಿಲ್ ಅನ್ನ ಎಷ್ಟೋ ಆಪೋಸಿಟ್ ಕರೆಂಟ್ ಎಲಿಮೆಂಟ್ಸ್ಗಳಿದೆ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ರೆ the net magnetic field should be summation of 2 dB sin alpha. Alva? 2 dB sin alpha with only two opposite current elements. If the entire coil is assumed to have many such opposite elements, B equals summation 2 dB sin alpha. Now substituting for this dB, summation 2, adhe idli sin theta chutney, that was, so dB is mu naught by 4 pi IDL by a square, and in the first calculation sin alpha was R divided by A. ಏನು ಸಿಕ್ತು? B equals summation 2. ಇದನ್ನ ಹಾಗೆ ಬರ್ದಿದ್ದೀನಿ. dB ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ವಲ್ವಾ ಎರಡು ಕರೆಂಟ್ ಎಲಿಮೆಂಟ್ ಇಂದ, mu naught divided by 4 pi IDL by a square. ಈ R by A ಎಲ್ಲಿಂದ ಸಿಕ್ತು? sin alpha I have calculated earlier, which is R divided by A. Or putting all constant terms together, mu naught by 4 pi is a constant. Yes, 2 is a constant. Have I changed the current flowing through the coil? No, it is a constant. Radius of the coil is constant, divided by a square into a cube. The distance between the element in the point is not changed. The only thing that may matter is length of the element. ಅದಕ್ಕೆ ನಾನು ಪುನರ್ವರ್ತಿಸ್ತಾ ಇದ್ದೀನಿ. DL, small length. So the moment I write this D, it means it changes. So summation DL. Now what is this summation DL? Again, if I observe the diagram, you have one element in the lower part of the coil, A dash, B dash, the other element AB in the upper half of the coil. So what should be summation DL? It has to be 2 pi r by 2. Why 2 pi r by 2? 2 pi r is the entire circumference of the coil. But I am considering two opposite current elements, half of the coil. So 2 pi r by 2. The circumference of the coil divided by 2, which is nothing but pi r for this circular loop. Therefore, B becomes equal to mu naught by 4 pi 2 IR divided by A cube into pi r, or B equals mu naught by 4 pi 2 pi IR square divided by A cube. But we know the value of A. Again, initially calculated r square plus x square to the power half. There is a cube here. So you have r square plus x square to the power of 3 by 2. So please to understand the magnetic field on the axis of a circular coil. When I consider a point on the axis of a circular coil is mu naught divided by 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2. This is a very conclusive expression. We work out quite a number of numericals based on this expression. And in vector form, vector B equals mu naught by 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2. Right hand side ali unit vector na introduce martini I cap. So I cap is the unit vector along the direction of px. Now, going to a special case where I assume the point P is at the center of the coil. So, in this special case now, I am assuming P to be at the center itself. Now, it is not at some distance from the center. It is at the center itself, which means x becomes equal to 0. Why is this x becoming 0? Because the point P is at the center of the loop itself. X is 0. So the expression reduces to, so this x becomes 0, 2 pi I r square divided by x 0 agoito, r square to the power 3 by 2. This square and square gets cancelled. R square r cube, one r is in the denominator. This is the expression for the magnetic field at the center of the coil. Mu naught by 4 pi 2 pi I divided by r. Axis r square plus x square to the power 3 by 2. Denominatorally, if it is at the center, x is 0, and this is the expression. Now, a very important note. If you observe the diagram, magnetic field is maximum at the center of the loop. 1 ಮಾರ್ಕ್ ಪ್ರಶ್ನೆ ಕೇಳ್ತಾರೆ, ವೇರ್ ಈಸ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಇನ್ ಅ ಸರ್ಕ್ಯುಲರ್ ಲೂಪ್ ಕ್ಯಾರಿಯಿಂಗ್ ಕರೆಂಟ್, and it is always at the center. And you see, it decreases on either sides of the axis. On the 2 ends of the axis, magnetic field decreases, but it is maximum at the center. And the direction of the magnetic field is along the axis of the loop. The direction of the magnetic field is always along the axis. So my dear students, in today's class, I've given you a very important derivation. Practice hard. As I told, without any confusion, this is a very frequently appearing question. Be thorough. In the next session, I come back with Ampere's circuit law. Until then, have a good time. Thank you.